You know when you have a rock star in the room, when you see the room filled and busy and excited, and definitely Demis is a rock star, as you all know. I made a few talking points. It's always a lesson in humility when reading a CV like the one of Demis. He was a child prodigy in chess. At age 4, he started. By age 13, he was at the master standard, okay? So that's a good start in life, I guess. He completed A-levels and scholarship level exams 2 years early, age 15 and 16. That's in the British system, but it's also telling. And Cambridge told him, "You're too young to come to Cambridge. Go do some video gaming." Okay. Now you can see how forward-looking Cambridge is. I'm not sure Cambridge told Demis to go into video gaming, but anyway, he took a sabbatical before starting to study. That's another message, please remember. So he joined a video gaming company, Bullfrog Productions. Then he went to Queen's College, Cambridge, completed computer science tripos and graduated in 1997 with a double first, another specialty from Demis and University of Cambridge. Then, okay, you would expect he would have stayed there, worked with, some fundamental scientists, but no, he went back into video gaming, okay? Now that's a career, I'm sort of thinking, why did I do only one thing with my life? And not only did he go back to video gaming, he founded a video gaming company, Elixir Studios, and then he actually returned to academia to obtain a PhD in cognitive neuroscience at UCL, one of the top places for neurosciences in the world, supervised by Eleanor McGuire. And he was trying to find inspiration in the human brain for new AI algorithms. I think this is extremely interesting because there is still something to be learned from the human brain. And he wrote a landmark paper, it's the first one he wrote, which established a link between the constructive process of imagination and the reconstructive process of episodic memory recall. Now, this is very interesting because the process of imagination is, I think, what ChatGPT doesn't quite do. Creativity is not there yet, but maybe Demis will show it to us today. After his PhD, he founded DeepMind with 2 colleagues. DeepMind, which is the top AI company in the world. It started very quickly, making headlines in 2016 after AlphaGo, the program they developed at DeepMind, that Demis was a chief architect, beat a human professional Go player in a 5-game match. Now, Go was considered to be much harder than chess. Chess was done years ago, as you probably know, and people didn't believe that actually AI-based algorithms would be able to beat Go, and Demis, sure enough, proved the rest of the community wrong. Then he went on to several other developments of that sort. I think the one that probably we are most interested in as scientists is AlphaFold. AlphaFold protein folding prediction. This is, I quote Demis, "This is a lighthouse project, our first major investment in terms of people and resources into a fundamental, very important, real-world scientific problem." And that's one of the reasons I'm so glad that EPFL is giving Doctorate Honoris Causa to Demis, because his true calling in life is to solve fundamental scientific problems. Some other companies you can think of that are active in AI mostly want to generate more clicks on ads or something else of that sort, even though they pay your bills, right? But I think, if I may say, but I think what I find extremely exciting at DeepMind and also the next company that he founded, Isomorphic Labs, is that Demis is really interested to solve fundamental science problems, and that's, I think, what we are all here to listen to. He has so many prizes. I tried to go through your Wikipedia page. It took several of my screens, so I decided not to list all his prizes, but simply to say that his work and the work of DeepMind got 4 times the breakthrough of the year mention in Science magazine, and that's interesting because essentially it's computer science applied to science problems that essentially transform science. And I think that's also something very important. I think computer science has a key role to play in the 21st century to really attack fundamental science problems outside of computer science, okay? Those of you at EPFL who know me, I have said this many times, computer science plays a central role. It's potentially the physics of the 21st century, and the demonstration is done by Demis Hassabis and his team and other people working at the forefront of artificial intelligence. Now, I'm going to finish by mentioning something that is very unusual, okay, which is the British novelist Ian McEwan in a book that you may have read, which is called Machines Like Me, which is an alternative history. So it rewrites history from the 60s to now, and you have Alan Turing, who is alive and works with his colleague Demis Hassabis to really change the face of the world by using AI and computer science for the good of humanity. I could make a quote here. I went up and looked the book, but in the interest of time, I suggest you read the book. So. Very good. So this being said, as I said, there is a small formal part here, which is the delivery of the Doctorate Honoris Causa of EPFL to Demis Hassabis. So I'll read the laudatio. I'll read it in English. So, École Polytechnique Fédérale de Lausanne confers the Doctorate Honoris Causa to Demis Hassabis in recognition of his visionary leadership in artificial intelligence and neuroscience, advancing the frontiers of science through his groundbreaking innovations in AI-driven scientific research. With this, I would like to hand over and congratulate Demis.
Thank you very much.
And we are going to...
Thank you. Thank you. Thank you very much.
Thank you very much.
Thank you. Thank you.
And with this, I let you take over using AI to accelerate scientific discovery. I have to excuse myself, unfortunately, but I will watch the video.
Thank you, Martin.
All right. Enjoy the show.
Thanks, Martin. Thanks. It's fantastic to be here, and it's an amazing honor to receive the honorary doctorate. And I've always, it's EPFL, I've always admired EPFL, and we have many collaborations with the Fusion Lab here, and also it's such an intellectual environment here. I've visited CERN nearby, and it's an amazing place to do science. So it's a real pleasure to be here to accept this award and give this talk. So I'm going to talk today about how I see using AI to accelerate scientific discovery itself. And I'll also give just a quick preview of how we got to the point we are now with working on things like AlphaFold. And then I'm going to talk a little bit about how I see things going into the future using AI to accelerate science. So we founded DeepMind back in 2010. It's almost like another age now, it feels, in terms of AI time. But it was only, of course, 13 years ago. And back in 2010, nobody was using, no one was really thinking about working in AI, certainly in industry. And it's kind of amazing to see what's happened just in a few years, going from 2010, where it was very difficult to raise any money to work on AI in industry, to now with billions of dollars going into AI projects. And it's been an incredible process to watch and be part of. And we founded DeepMind in 2010 because we thought a lot of progress could be made if we brought together hardware advancements, algorithm advancements, and some knowledge about how the brain worked, and get some inspiration from the brain for certain types of algorithms and systems, and bring that all together with amazing engineering. And we felt back in 2010 that some very fast progress could be made. The kind of progress that we've seen, although even that, I think, has been surprising to even those of us in the industry. So we tried to kind of form this Apollo program-like effort at DeepMind to bring together multidisciplinary groups of amazing researchers and engineers to make the most progress we could as fast as possible. Our mission statement was to try and solve intelligence and then use it to advance science and benefit humanity. By solving intelligence, what we meant was trying to understand the nature of intelligence and then recreate that in an artificial construct. That, I think, is the science of AI. So we started off, our first big result was with classic Atari games from the 1970s. And our first system called DQN, Atari DQN, was our first sort of successful big system, really. Back in around 2013, we got this working. What it was able to do is demonstrated, I think, the power of learning systems. It was the first really big system that was an end-to-end learned system. So the innovation here was that we didn't give the rules of the game or the criteria of how to get points or anything to the system. All we gave the system was the raw pixels on the screen, and it had to figure out everything else from first principles, and being told the goal was to maximize the score. That's it. Had to figure out the controls and how to get points and so on. And so at the time, this was pretty astounding because no one had ever sort of done something at this kind of scale. 100 by 200 pixels, so the inputs was 20,000 pixels, and that was pretty huge for any kind of neural net or learning system. This DQN system went on to kind of learn to play any Atari game to better than the best humans can play and get them to sort of maximize the score. So for us, this was a watershed moment. I think quite a watershed moment in the field in terms of what these learning systems might be able to do if we trained them in the right way. So then, as Martin mentioned, probably one of our biggest results, certainly the biggest one we had in gaming, was AlphaGo, which was our system in around 2015, 2016 that we built to learn how to play Go through a self-learning process that I'll describe, and kind of famously managed to beat the world champion at Go, the legendary Lee Sedol, the South Korean grandmaster. And why is Go so much tougher than chess and other games to play? Well, partly it's the complexity of Go. Humans have played Go for thousands of years now. It was invented 3,000 years ago. It's still as popular as ever today, over 40 million active players. And one measure of the complexity of it is that there are around 10 to the power 170 possible board positions in Go, which is far more than there are atoms in the observable universe. So there's no way to kind of brute force search through this incredibly complex combinatorial space in order to figure out what the right moves are. And the other extra thing that's hard about Go is then you'll see a Go board on the right there, is that it's quite an esoteric aesthetic game. It's one of the things that makes it beautiful. And it's very difficult to write heuristics or rules down about how to evaluate, how a machine might evaluate a position and evaluate who's winning. So-called evaluation function, which is critical to machines playing these types of games. And in chess, it's because it's a material game, it's a lot easier, and a calculation game, it's a lot easier to actually specify what these heuristics are. But in Go, that's kind of impossible. So people have spent 20 years prior to AlphaGo trying to handcraft these heuristic systems to kind of describe the aspects of a Go position. And one of the issues is that because Go is such an intuitive game, even the top human players, grandmasters like Lee Sedol, they don't really think about it in terms of calculations and rules. It's much more about feeling and intuition, which are traditionally two things that you would say are difficult for computers to do. So AlphaGo went on to win the match 4-1 in Seoul in 2016. Pretty famous match. It became over 200 million people watched the match around the world. And there's a fantastic YouTube documentary on it, award-winning documentary on it, if you're interested to see how that played out. But the interesting thing was not only the fact that it won the match, of course, but it was also how it won that was pretty surprising. And actually, AlphaGo created new strategies in Go that had never been seen before, even though we've played this game for thousands of years. And the most famous one of that was move 37 in game 2 of the 5-game match, which astounded the Go world and is still being sort of studied today. And move 37 is that black stone circled by the red there on the board. And this early in the game, it's sort of unthinkable to play that near to the center of the board. It's sort of not considered to be a good strategy at all. And in fact, when the professional commentators were commentating live on this game, they thought there was an error in the computer system in order for it to play there. So it was such a surprising move. And it's interesting, actually, just to touch on, and maybe we can touch on this in the Q&A, is what does this mean about creativity and intuition, these sorts of aspects that we think are very cognitive. And I think when I reflect back on this, I would say that there are at least 3 levels of creativity, and perhaps AlphaGo and systems like that, the current systems we have, exhibit the first 2. So if we think about interpolation, that's, if you imagine, you ask us one of these generative systems to imagine, show a picture of a cat, maybe it will have seen millions of pictures of cats before, and then it does some kind of interpolation or averaging of all the cats that it's seen, and then it produces a sort of prototypical cat and outputs that as an image. So, that's an original cat. It doesn't exist in the training set, but it's a simple sort of matter, relatively simple matter of kind of averaging across the exemplars that it's seen. The second type of creativity at the higher level is extrapolation, where you sort of sample the distribution. And so in AlphaGo's case, maybe you look at all the human games that have been played online, and you start building up patterns of what are reasonable things to do in Go, reasonable positions. But actually, you then not just simply average what you've seen, but you actually extrapolate these motifs into new parts of the distribution that perhaps that are not in the training set, beyond the training set. And I think this is what Move 37 is, and AlphaGo has clearly, and systems like this have clearly demonstrated. And I think that's very exciting if you think about the potential for that in science, to extrapolate beyond, make models of the current distribution we can see, and then extrapolate to come to new conclusions and new ideas that are beyond the boundaries of what we have data for. And then finally, and I think today's systems don't do this, maybe we can call it invention or out-of-the-box thinking, which I think is an even higher level of maybe abstract creativity that, of course, we as humans do effortlessly, but so far I would say machines don't do. And I think the easiest way I can give you an example of that is, of course, AlphaGo was able to make these amazing creative strategies in Go, but it couldn't invent Go, right, or invent chess. That to me would be a new level of invention. And I don't think that's impossible. I think that's just partly actually maybe the limitations of the current systems, but also the limitations of the way we're able to describe the goals to these systems. So, I think if you were to get a human game designer, like the sorts of things I used to do, to try and come up with Go from scratch, you might say something like, come up with a board game that is beautiful aesthetically, that takes 5 minutes to learn the rules. There's only a couple of rules for Go, but takes maybe multiple lifetimes to master, and you complete a game in maybe 6 hours, so within a human life afternoon, so to be convenient. So maybe you would specify these kinds of goals, and then Go would be an answer to satisfy those goals. But you can see that would be very high-level specification if one was to do that, which so far our systems wouldn't, I don't think, be able to cope with that. So just to explain a little bit about how AlphaGo works, and I'm actually combining several pieces of work here together when I describe this. This is sort of simplified description of how all of these types of systems work. This includes AlphaGo and its successor programs, AlphaGo 0 and AlphaZero. And AlphaZero actually is a kind of general games playing system that can play any 2-player board game, a perfect information game, better than world champion level. And so the process is actually quite simple to describe. So you start off with a neural network, initialized neural network that basically plays randomly. And you can think of that as version 1 of the system. And it plays around 100,000 games of whatever board game it's playing. That creates a data set of these 100,000 games and all the positions in those games. And then you train a second version of the neural network on that data set. And what you're trying to do here, the neural network's got 2 jobs. It's got to predict the probability of who will win from that particular position, and how likely they are to win, whether it's which of the 2 sides will win, and also what are the more probable moves that might be tried in a certain position. So that's the sort of 2 prediction jobs of the neural network. Then, when you've trained version 2 on this version 1 data, you have a little 100-game tournament, and you match off version 2 against its predecessor. And you have this 100-match game, and then if it wins a significant amount of time, we set the threshold to be 55% win rate. Then you replace the current system with the new one. So you replace version 1 with version 2. And then you do this whole cycle again. You play another 100,000 games, but this time with version 2 playing against itself. You generate a new data set, slightly higher quality because version 2 is slightly better than version 1, and then you train a version 3, and that matches off against version 2. Now, if version 3 it turns out not to be better than version 2, statistically better, then you continue to generate another 100,000 samples with the current version 2. So you end up creating 200,000 games then for the new version 3 to be trained. And eventually, the new version will beat the old version. And if you do this system in terms of Go 17 times, different games require different amounts of cycles, you go from playing randomly to better than any entity on the planet has ever played Go. And it's quite a thing to watch live, especially in something like chess, which I know well. You know, you start the process off in the morning at breakfast, you know, around coffee time at 11 a.m., you can still beat the system, or, you know, and then by lunchtime, it's better than world champion. It's actually quite amazing to actually watch that live as you're sort of, you know, going through your morning. So it's quite a thing. And it's very visceral if you play chess or play one of these games to see that live in front of you, that whole process. So what's going on here then? Well, effectively, if one thinks of a Go tree as the tree of all possibilities, and you imagine each node in this tree is a Go position, so you're currently in this, you know, the current position is the top of the tree, and you've got this enormous, you know, set of possibilities from each position, you know, the 10 to the 170 possible positions, and you've got to find this sort of classic needle in a haystack. How do we decide what the optimal strategy is, the optimal move to play from this kind of position in a very finite amount of time, you know, maybe 1 minute of thinking time? So clearly it's not tractable to do this in any kind of vaguely, you know, any kind of brute force way or exhaustive way. So what we're basically doing is guiding the search with the model. So the model is coming up with most probable moves and the kind of most interesting moves to look at, and therefore guiding the tree search to be very efficient in the budget that it uses, the sort of Monte Carlo tree search. Maybe it can only search around 10,000 moves per decision, and it's got to apply that very limited budget of search budget to most appropriately to the entire search tree. And then when it runs out of time, of course, then it outputs the best plan, the best tree that it's, the best sort of path that it's found up till that point. So we've been pretty lucky and using games, and we started with games. I mean, partly obviously my background in games, and I try to utilize every single strand of the things I've experienced in my career to bring them together, to always make use of them. And I always had in mind, even though, as Martin was describing, all these different things I did earlier in my career, from probably around 14, 15 years old, I had already decided that AI was going to be my career, and this is what I wanted to do with my life. And then all the other things I picked to do, from the PhDs to writing AI for computer games, was sort of in preparation, if you like, for doing something like DeepMind. And then we made use of all this games knowledge, and we have quite a lot of amazing games engineers, ex-games engineers at DeepMind who work on these simulations and work on these programs. We worked on games because we thought it would be the fastest way to make efficient progress with testing out algorithmic ideas. And that turned out to be the case, and we were fortunate to make a whole bunch of big breakthroughs. I've just talked about DQN and AlphaGo and AlphaZero, and then we culminated in this program called AlphaStar, which beat the grandmasters in the most complex computer game, strategy game called StarCraft 2, which has all sorts of other challenges from board games, like partially observable environment, and it needs long-term planning and other big challenges. So with that, games has been phenomenal for making progress over almost a decade worth of work to get the algorithms to a point where they were sophisticated enough to be applied to challenging real-world problems. And of course, that's problems, commercial problems and industrial problems, and pretty much every system that you use now at Google has a piece of DeepMind technology in it. From the way the massive data centers are cooled to the voice on any of the devices that you speak to. The Google devices you speak to use WaveNet, which is the world's best text-to-speech, most realistic text-to-speech system. A piece of DeepMind technology is sort of in almost every service. But for me, my personal passion, as Martin was saying, is to eventually, the plan was to use AI as this incredible tool, almost like the ultimate tool for helping accelerate scientific discovery. And I think in the last few years, maybe 2, 3, 4 years, I think that's become possible. And I think it's a really exciting time now in AI to do this, to bring over all of these amazing ideas that were developed in areas like games and other theoretical domains and bring that to real-world important problems. So for me, I always had my eye on, and I learned about the protein folding problem, and I'll describe that very briefly for those of you who don't know what it is. In my undergraduate in the 90s at Cambridge, I had quite a lot of biologist friends there, and one of them was particularly obsessed with this protein folding problem, and still works on protein structure today in Cambridge as an academic, and always sort of thought, first of all, that it would be tractable one day, but also that it would be enormously important if one could solve this problem. And I've always loved this problem. I've always thought it would have sort of filed it away in the back recesses of my mind as one day to come back to as we progressed with AI, because I thought it would be very suitable for AI for a number of reasons. So the protein folding problem is quite simple to explain. Proteins, for those who don't know, obviously the workhorses of biology. They're essential to all life. Everything in your body is pretty much supported by proteins. And of course, we'd like to know their function. And their function is partially specified by their 3D structure. So if you imagine the protein is specified by its amino acid sequence, which you can loosely think of as its genetic sequence, and then in nature it folds up into this 3D structure, and that's what kind of governs its function. Now, determining the structure of these proteins often takes many, many years. If you're going to do this experimentally, a lot of painstaking work. Perhaps many of you in the audience work on these things. And the rule of thumb that again, biologist friends have always told me is it can take a whole PhD, 4 or 5 years to maybe even crystallize and figure out one protein structure. So it's really a lot of work. And Christian Amfindsen, very famously in his 1972 lecture, for his Nobel lecture, speculated that the 3D structure of a protein should be fully determinable by the amino acid sequence. In other words, we should be able to predict this 3D structure immediately based just solely on its sequence. Now, of course, that then triggered literally a 50-year kind of grand challenge in biology, and people have been trying to make progress on this ever since, and it's obviously a whole field in itself. So why is this such a hard problem to solve this structure prediction problem, the structure prediction problem of the protein folding problem? Can it be solved computationally, and why is this such a hard problem? Well, again, according to a contemporary of Amfindsen, Levinthal's paradox, he sort of back of an envelope calculated there's roughly 10 to the 300 possible conformations that an average protein can take. And yet, obviously, the paradox is that in nature, obviously spontaneously, within milliseconds in many cases. So how is this possible? How does physics solve this then, is the big question. And the other reason we picked this problem is that there's a fantastic, really well-run competition called CASP that runs every 2 years, and it's been running for nearly 30 years now, and it's considered to be the gold standard benchmark in protein folding to test the best computational systems. And it's a blind test, so experimentalists submit their structures just prior to publishing for the competition, and computationally you have to submit your prediction, and then later on they reveal the ground truth structure, experimental structure, and then you compare the ground truth against your prediction. And usually for every cycle of the competition, they have around 100 proteins that they've collected like that they sort of withhold publication of. So AlphaFold 2, as many of you know now, did achieve atomic accuracy. So this is accuracy of the computational prediction to within the width of an atom, which is what we were told was the tolerance for it to be useful for real-world biology and chemistry. And we achieved this accuracy at CASP 14, the 14th edition of CASP in November 2020. And if you look at the progress of CASP, and the winning team, this is the score of the winning team in each of the editions back the prior 10 years to we entered, so from 2006 to 2016, there'd been almost no progress on the hardest category, so-called free modeling category, where there are no prior templates for these proteins. And you know, this score on the y-axis is you can think of it as roughly, it's called GDT, but you can think of it as roughly as the percentage of residues you've got accurately positioned to within a tolerance, a very tight tolerance. And so they were stuck around 40 pretty much, which is not useful in any way for experimentalists. It's far too large in errors. And in 2018, we entered for the first time. We started this work in 2016. The whole project is probably the most complex project we've ever worked on. And we started it literally pretty much the day after we came back from Seoul, from Korea, from the AlphaGo match. This was the next big project we took on. And AlphaFold 1, we entered into CAS 13, and for the first time ever, we sort of entered a system that had cutting-edge machine learning at the core of the system for the first time. And it improved accuracy immediately from the previous sort of winning scores by around 50%, as you can see here. And then we totally re-architected AlphaFold 2 with a whole bunch of new innovations and taking the learnings from AlphaFold 1, and then that finally reached atomic accuracy, which led the organizers of CASP to declare that the problem had been, in inverted commas, solved. So how does this look? Well, AlphaFold takes many iterative steps towards solving a protein structure, and you can see this enormously complex protein on the left here. It's just one example of one of the structures that AlphaFold predicted, and you can see the ground truth in green, and in blue is the prediction, and you can see on the right-hand side how the different iterative steps AlphaFold sort of settles on a final prediction of the structure. And it's still amazing to me when I watch these things and see the complexity of and the beautifulness actually of proteins. How this can be computationally predicted is still pretty astounding to me. So then we went on to obviously publish all the methods. We open sourced the code, and then we decided, like, how are we going to share this with the world so that the biology community could make best use of it? And we actually decided that the best way to do this was to create a database, freely available database with free and unrestricted access to all the structures that AlphaFold predicted. And we did this in a great collaboration with EMBL, EBI, European Bioinformatics Institute, just up the road from us in Cambridge in the UK. And normally when you do these types of systems, you set up a server, and then people submit, experimentalists submit their structure they're interested in, their sequence they're interested in, and then you predict a structure and you send it back maybe a few days later. That's the normal way people used to do, used to provide access to these systems. But because AlphaFold 2 was so fast as well as so accurate, we realized that actually over the course of a year, we could actually just fold every protein known to science. So that's around 200 million, depending how you count it, obviously growing all the time. And so we ended up over the course of a year folding every protein there was, and that we could get our hands on in the UniProt database, and then we made that available. Of course, before we did that, just as a side note, and I'll come back to this at the end, we always have safety and ethics at the forefront of our mind of every work that we do. So before we released such a massive database, we consulted actually with over 30 experts in many relevant fields, of course, biology, but also biosecurity, bioethics, pharma, and also human rights too. And from that, we actually made some slight modifications to what we were going to put out there, but the overwhelming feedback from all of them was that the benefits far outweighed any perceived risk. So since then, so it's been out for, AlphaFold's been sort of available for a couple of years now, or maybe getting on to 3 years, and already it's been incredibly sort of gratifying to see how many things that AlphaFold has been applied to, and the wide range of important problems it's being used for. And here's just a small sample of those problems that have been tackled using AlphaFold predictions, and there are many more on our website, unfolded.deepmind.com, where you can see many more sort of testimonies and examples, case studies of how AlphaFold's been used. And I'll just highlight a few here. It's been used by the University of Portsmouth to design sort of plastic-eating enzymes to tackle plastic pollution. It's been used all over the place in big pharma for drug discovery, and also in academia, antibiotic resistance and malaria vaccines, and also neglected diseases, which is a very important part of our mission, neglected tropical diseases like leishmaniasis and dengue that we think often don't have a lot of investment in from pharma, that the NGOs that work on these types of diseases, it was great for them to get an immediate leg up by seeing the structures of the proteins that they were trying to target, and obviously get straight into drug discovery. And then it's also being used in fundamental research too, for example, helping with finding the structure of the nuclear pore complex, and also designing things like molecular protein syringes for delivering payloads into the body. So incredible diversity of different things. And this is always what we hoped for working on this problem of protein structure prediction, was that if it could be done, it would unlock, if we were in this new world of sort of protein structure abundance, it could unlock all these downstream amazing pieces of research. We've been very lucky as well in the terms of it's been recognized, AlphaFold, by very nice accolades like Breakthrough of the Year from Science, Method of the Year from Nature, but also the amount that it's being used has been incredible. So over 1 million researchers and biologists have used AlphaFold in the databases from all around the world, pretty much every country in the world, and the methods papers had over 10,000 citations already. So just in terms of the bigger picture then, if I step out a bit now and start looking at where is all this going, I like to use this phrase of science at digital speed. And I think we're going to start seeing this more and more now. And what do I mean by that? Well, I mean science at digital speed in 2 different ways. First of all, if you take AlphaFold, it's an extremely fast solution, of course. So you can get the structure of a protein in a matter of seconds instead of potentially, months or years if one would have to do that experimentally. So the solution itself is very fast, and that allows us to scale up to, 200 million proteins. But also the dissemination of that information is also at digital speed, because it's a technical solution. So the moment you've kind of built the algorithm and you folded all the proteins, we can then put it on the database, and everyone in the world can then access it just with a simple keyword search. So if you compare that to an experimental breakthrough, amazing ones, they still made me take a decade it can take or more to propagate through training PhDs on those systems, building the right equipment in order for those to work, and training people to use those new techniques. And instead of, something science at digital speed is able to propagate almost immediately, just like any other piece of software or technology. So I think this is maybe the first example of that, but I think it's an interesting phenomenon that I think we'll start seeing a lot more of. And just following up on that theme then, if I like to think of that maybe we're entering a new era of what we like to call digital biology. And I think if you think about biology at its most fundamental level, I think we can think of it as an information processing system. So albeit a very complex emergent one. And if we think of it in that way, then in the same way that maths was the perfect description language for physics and physics phenomena, perhaps I think AI could end up being perfect for this type of complex emergent regime to describe and model what's going on in biology. I think it may turn out to be the perfect fit for AI. So I'm hoping that AlphaFold is a sort of proof of concept, if you like, and when we look back on it, maybe 10 years from now, it won't just be this isolated success story, but actually we'll see that it heralded this new era of digital biology. And we've actually followed up on this ourselves by starting a new spin-out company called Isomorphic Labs to try and reimagine the whole drug discovery process from first principles with AI. Of course, the protein, AlphaFold and the protein structure is just one very small aspect of doing drug discovery, right? Very one small piece of the whole puzzle, an important piece, but nonetheless just one piece. So we need to fill in all of these other modules that are required actually to do drug discovery, from target discovery to designing chemical compounds and designing drugs. So Isomorphic's approach is to sort of try and tackle these most fundamental problems in drug design with this AI-first or computational-first approach. And then we combine several advantages from different areas. We have the new company has close collaborations with DeepMind and their AI and science teams there. It also has huge resources and funding from Alphabet, the parent company of all of these companies, to allow us to kind of think long-term and ambitiously, and so we can really try and go after the fundamental research to begin with to build this platform, this general-purpose platform, a bit like I showed you with games at the early part of the talk. And we also get to utilize, of course, all of Google's enormous sort of infrastructure, which, of course, is incredibly important for computational and AI approaches. And we get to do all of that, so sort of take advantage of a big company backing, but within the context of a fast-paced and nimble startup environment. We pulled together this world-class multidisciplinary team. I'm a real believer in multidisciplinary research work. We've always had that at DeepMind, and we have that also at Isomorphic, incredible team across AI, chemistry, bio, physics, and engineering. And we were lucky enough to have this amazing scientific advisory board that's been set up with several Nobel laureates. And excitingly, we have offices in London, but we've also opened an office here in Lausanne, actually, in the Innovation Park, just locally, and have some of my colleagues here today from the Lausanne office, which is amazing. So another great reason for me to be visiting. So that's where we're going now, and that's where I see these types of techniques, and I think we can, at Isomorphic and at DeepMind, we're trying to create maybe half a dozen more AlphaFold-like systems, but in different parts of the chain that's required to do drug discovery. So maybe if I finish now by just taking a further step back and looking at the holistically about all the work that we've done over the last decade plus, and I think it goes back to that search tree I was showing you. I think a lot of AI can be kind of thought of in the most general way, in this way, that you have these enormous combinatorial spaces, whatever the problem is that you're trying to solve. And there's huge numbers of combinations that can be that need to be searched. And what you do to make that tractable is you learn a model of that environment, either directly from data or from simulations in some cases, or ideally you have both. And then you use that model to guide the search in a tractable way according to some objective function. And I think it's pretty simple to describe, but actually, if you think about AI in this way, I think and actually start looking for problems you can apply it to, it turns out this is a very general solution. And actually, many problems can be modified to fit this pattern. So here's the Go tree again, with all the search tree and how it finds this optimal plan and the optimal moves. And now if we replace, this is obviously a cartoon, but it just gives you the idea. If we replace Go positions now with chemical compounds, one could imagine building up new drugs or new chemical compounds that are useful for things using some kind of search like this. But in this case, the model will be modeling chemistry space and chemical properties. We've actually had a pretty amazing couple of years now in sciences, applying these types of systems and other systems to all sorts of scientific domains, not just biology. We've done some great work in quantum chemistry, in pure mathematics, solving some important conjectures in collaboration with some amazing Fields Prize mathematicians. Fusion here collaborating with a fantastic team here, EPFL, to control plasma in a fusion reactor, and then work on genomics, weather prediction, all sorts of domains. And I think it's just the beginning of what we're going to see, this sort of real flourishing of applying AI, this kind of general purpose AI, general purpose learning systems, to pretty much every branch of science. So just then a word on pioneering responsibly and how is one undertake this work carefully and ethically. It's a very, very exciting time. I think AI has the incredible potential to help with almost all of humanity's greatest challenges, from curing diseases to energy and sustainability in the environment. I think AI has the potential to help with all of these problems. But of course, it's an incredibly powerful technology, and it can be used. It's a dual-purpose technology. Depends on what we, as society, decide we're going to deploy and use it for, and how we build it. And it needs to be built responsibly and safely, and to be used for the benefit of everyone. And as I mentioned from the beginning, even back in 2010, when we were in a tiny little office space in an attic in London, we were planning for success. When we started in 2010, we imagined a world like we're in today, and actually even beyond where we're going to be in the next 10 years. And we imagined that, and so therefore, if one were to imagine this kind of world, you would be thinking about ethics and safety from the beginning, and that's what we were doing. And it's been central to our mission from the start. We've always had an ethics charter and an ethics committee, and that's actually evolved now into the whole of Google having their published AI principles. So now we're part of Google. We help across the board now, across the whole company, with applying these principles correctly everywhere where we deploy AI. And we continue to try and provide this thought leadership on AI strategy globally, risks and ethics and safety for the whole research community and beyond. So how should we pioneer responsibly? This is what, obviously, I'm sure you all agree, this is what we should do with this type of technology. And my view is that we actually have a way to approach this, and we call this artificial general intelligence, when we get to human-level cognitive capabilities across the board with these systems. And I think we're approaching that pivotal moment in human history quite rapidly. Maybe it's a few years away. And my view is that we should not move fast and break things, which is the kind of Silicon Valley mantra that, of course, is very successful in building social media and huge companies and getting very great growth for applications and technologies. And it's served us very well. But I think when it comes to something as consequential as AGI, I think instead we should be sort of looking towards the scientific method, which of course you'll all be familiar with here. And I think that's the approach that we should be taking with these kinds of systems. So thoughtful deliberation, hypothesis generation, and rigorous testing of those hypotheses in carefully controlled environments and conditions, detailed analysis, updating rapidly on empirical data, perhaps with external review, and all with the aim to get a better understanding of these systems before we deploy them in the wild. And I think the key thing here is sort of not so much not to move fast, because I think we need to move at pace with these systems because of the enormous potential they have, but ideally not to break things, right? Or as far as possible, not to do that with and use as much foresight as possible. So I think a transformative technology like AGI requires exceptional care. And our view at DeepMind at Google is that we need to be bold and responsible with this technology. And it really is an and I think although those two words, there's some tension there, I think it's a good tension to have. So I'll just finish then by saying if we realize the full potential of AGI and build these types of systems, I think they'll be the ultimate general purpose tool to help us as scientists understand the universe and perhaps our place in it. Thank you very much.
Thank you very much, Demis, for this impressive demonstration of the power of the tools you've built. We have some time for a few questions for the audience. So the house rule is you need to come to the standing microphones that are situated here and there. Make a line if you have, if many of you wish to ask a question, and we'll take them one after the other in the time that we have at our disposal. I have maybe one first question.
Yes.
While people come into the line. You've shown how it worked, your system on Go, on video games, and then what kind of mental shift did it take to someday say, hey, it would probably work on proteins as well?
Well, for me, maybe it looks like that if you, I think the missing piece of information, if you look at my career, is that I had already decided, and actually through chess, originally it was games that got me to AI, because most of you too young in the audience remember this, but when I was playing chess in the 80s, sort of semi-professionally when I was a kid, I was using chess computers to train on. And originally they were these physical boards that you would actually press the squares on, and they had little LED lights. And I was fascinated. I must have been about 8, 9 years old when I got my first one. That how were they programmed? This machine, this bit of plastic in front of me. How was it playing chess and helping me train? And I think I kind of determined at that point that I wanted to learn actually how to program machines to do that. And in some ways, that was more fascinating even than the game itself, was actually how these systems were programmed. And so then I went into professional computer games development, but if you look at all the games that I made, Theme Park, all of these things, actually the common core theme was it had AI as the core part of the gameplay. And again, that just reinforced, I saw something, my probably most famous game I wrote was Theme Park when I was around 17 years old, and it was designing your own Disney World. And then little people came into your Disney World theme park and played on your rides and designed the park. And they all had AI controlling them. And when I saw people enjoy that so much, to how the game reacted to the player, I sort of realized how much AI could bring to the world. So then everything else I've done and sort of collected was with this in mind, where what we see today in mind.
Brilliant. Thank you very much. So we'll start on that side. Please make short questions.
Hello. Thanks for an excellent talk. Your body of work and journey has been very inspiration to me. So my question is the following. When you are building for the first time these complex systems like AlphaZero, I'm pretty sure many people have tried before and failed. So for you, what was the conviction or the inspiration that somehow we'll build these systems that will turn out to be amazing breakthroughs? So can you give us a sneak peek into?
Sure. So back in perhaps when I was doing my undergrad, one of my really good friends at Cambridge was this guy called David Silver, who ended up he's one of the best reinforcement learning people in the world, but also he ended up being the project lead on AlphaGo. And we used to talk about, and he was also part of my first games company, he was the CTO. And we always used to think about Go, actually, which I learned at Cambridge. There's a really good Go club there, and we both learned Go there. And we were always fascinated by how would we program that. And we tried, actually, in the early 2000s to do it in the way that the classical chess programs are being written, with these heuristics and search. And it kind of gets you nowhere. You can't even get to strong amateur like that. So we sort of shelved it for 10 years, really, and we decided then that actually you needed a learning approach. That just confirmed our intuition that there's no way that we can enumerate out all the heuristics for something complex like that, even something like Go, let alone more general things than that. I think that reinforced our opinion that you needed learning systems and that were general.
Thank you.
Thanks.
Thank you very much. Let's take a question from the other side of the room.
Hello. Thanks for the great presentation. Fascinating to see what's going on in this domain. Especially, I'm glad to see that there's progress in terms of drug discovery. And I can imagine that investors are queuing up. And so we also know that in this particular domain of industry, not all or let's say some of the larger investors have proven that sometimes colossal profits are more important than any ethical considerations. So my question is, how do you at Isomorphic Labs think about the monetization aspects, and do you make any promises in terms of enlarging access to medication for the entire human population, including the large part and the majority who currently don't have it?
Yeah. Well, look, I can't make any promises, but I can definitely tell you that the intention is, and the idea is that if this all works out, with this computational approaches, which should be maybe even an order of magnitude faster to develop new drugs, maybe instead of 10 years, 1 year, you could imagine, and therefore maybe an order of magnitude cheaper to develop those things, perhaps more, perhaps even 2 orders of magnitude is possible. And then I think if you have both those two things, it's far easier to distribute that and work on many, many diseases, not just first world diseases in wealthy countries, where I think pharma traditionally has to make its sort of calculations, and actually you can do a lot more. And I think we've seen the beginnings of that with AlphaFold, as I mentioned. One of the places we collaborated with, I think they're actually based in Switzerland, was the DNDI, Drugs for Neglected Diseases Institute. It's part of, I think, WHO. And we folded, all of the proteins in all the diseases that affect mostly the developing world and the poorer parts of the world, but affect millions of people there, hundreds of millions actually, but are generally underserved by the current pharma industry. So I really hope that the work we're going to do is going to allow us to broaden that access, and then maybe also make, act as a role model to pharma to do more of that too.
Like open sourcing medication.
Yes, for sure, exactly. For these sort of diseases that affect the developing world more. Yeah.
That would be wonderful. People are also queuing up to ask questions.
Yes,
so please
sure, we should.
So thank you very much for the talk. So quick question. So what happened? What turned out to be harder than you thought, and what turned out to be easier than you thought over the last 13 years?
Yeah. So. In a way, there were so many, it's kind of hard to remember because there's so many different projects we've done, and at all times there were difficult moments. I think one of the hardest moments was after AlphaFold 1, trying to push AlphaFold 1 to reach atomic accuracy. So that's the first thing we tried to do in roughly 2018, was push that first system. And after around 6 months, we realized it couldn't go any further, and we had to go back to the drawing board and use what we'd learned, but actually re-architect everything. And for a long time, probably another 6 months, maybe even a year, the new system, AlphaFold 2, was worse than AlphaFold 1. And you have to be very confident and brave and persistent when you go through those periods to just trust that it's going to come back, and then it has more potential to go further because of the way you've re-architected it. So that was with AlphaFold 2, and then maybe on what's gone easier, I guess you could imagine language modeling has perhaps surprised everyone, I think, on the whole research community, including us, of how that maybe relatively easy that was once transformers and RLHF had been invented, 5-6 years ago.
Thank you.
Thanks.
Thank you. We have 5 more minutes to go, so I'm afraid we won't be able to take all questions.
Yeah.
Time moves very fast, but please, next one.
Okay, so first off, thank you very much for your work, amazing. And I want to ask if there are any plans to address inequality in regards with the alums or students from non-elite universities, which usually have less funding, less collaboration opportunities, less visibility on their work. So do you plan to address that? Because it usually is also an indicator of socioeconomic circumstances, and usually most of the inclusiveness work is regarding the individual circumstances and not so much the context of the person.
Yes, we care about that very much, and actually we have very big diversity and inclusion efforts at DeepMind, and we sponsor, it's mostly in the UK currently, but we're going to try and make it more international, hundreds of master's students scholarships from underrepresented backgrounds, both socioeconomic and other types of underrepresented backgrounds. And we've encouraged the UK government to do that. So actually now they provide thousands of scholarships at the master's level for machine learning. So the idea, I think we picked master's level because it's almost like a conversion course from STEM undergrad, science undergrad or maths undergrad, and then getting them into machine learning and then either PhDs or into industry. So that's worked really well. We've also sponsored, funded several chairs in machine learning at many of the universities in different parts of the regions of the UK and also internationally. And then recently, we did a $5 million sponsorship to the African Institute of Mathematical Sciences to kind of train the best students in Africa who are already in the mathematical society in machine learning. And actually we've seconded one of our senior research scientists to be the director of that in South Africa of the whole institute for the next, I think, 5 years. So we're trying to do a lot of things around that, but more needs to be done.
Thank you very much.
Great, thank you very much. Next question, please.
Yes, thank you so much. And more than 10 years ago, you bet on something that few people believed in. And now AI is something that everybody is jumping in. So what do you imagine AI can do, not for science, but also for humanity in general in the future? How far it can go?
Yeah, I think I've always imagined there's almost no limits in some way to AI, because if you look around us in modern civilization, how did we create modern civilization? What we see, all the amazing things we see around us, it was with intelligence, right? So, and I think if you think back, if you do thought experiments, like you imagine going back to pre-agricultural era, and you talk to a tribesperson then about, one day we'll build Manhattan in New York and fly over in a 747 in 10 hours. It would be unthinkable. And I think, but human intelligence has done that. And I think that there'll be almost as big another revolution with these tools and helping us solve all incredible problems that we think are quite intractable today, maybe, like energy sources, material design, I'm thinking, as well as biology and drug design, curing hundreds of diseases. I think that's all within reach. And then I hope we would have a much more, you can call it radical abundance, much more equality in the world, and lots of these huge problems, some of which we've created for ourselves as a society, like climate, we'll have really great solutions to, with AI helping the best experts in the world to solve these problems.
Thank you.
Thank you very much. One here.
Hello, I'm Leon from Open Knowledge Association, and I have a question linked to the use case of infrastructure. Do you intend to use infrastructure AI in the infrastructure field, for example, for waste management, or can be simulation for the buildings or stuff like this?
Yeah, great question. I'd love to do that. I think there's huge potential in using AI to optimize existing infrastructure, transport, power grids, and so on. I think to get maybe even like 30–40% more out of them. That's what we found with the data centers. We optimize these massive data centers that Google uses and powers all search, YouTube, and so on. We save 30% of the energy from the cooling systems by using AI to control them. And they already were quite optimized systems. But you can even imagine things like shipping lanes. I mean, there's a huge amount of pollution is caused by that, and just being more optimal on logistics, as well as inventing new solutions like the plastic eating enzymes I mentioned, or designing ways to deal with waste, recycling. I think all of that AI could help that that entire industry actually if we embed it in there.
Thank you.
Very inspiring. Thank you. I'm sorry to be the nasty timekeeper, but this will be the last question.
First, thank you for the very nice presentation. Really looking forward to the progress of science over the next decades. My question is, how do you see the role of open source in AI over the next decades, and what do you see to be the best approach to AI in terms of balancing the risks of AI? Of course, it's harder to maintain safety when everything is open, but at the same time, letting everyone contribute and using all of the brains in the world for this amazing development.
Yeah. No, fantastic question, and a complicated one, right? As you might expect, you've actually set that, you've explained that in your question. So up till now, as you'll know, like DeepMind's pretty much published everything we've done, all our Nature Science papers, and open sourced AlphaFold and other things. I think it's got to be on a case-by-case basis. As the systems get more and more powerful, more and more general, the problem is if you just open source naively these systems, bad actors can, whether that's individuals or nation states even, can obviously access it, militaries and so on, the same as scientists. So it's a complicated problem because obviously one would like to do open science and And of course, things progress much more quickly like that, and it's good to get external review of your systems, but how do you also restrict access to bad actors who might want to use it for bad means? So I don't really have a full solution for that. Maybe there'll have to be more access to like individual departments or universities or academics that are known to be working on the right things. Perhaps that's one way of doing it with the latest frontier models. Or, but it's not this is a current debate that's going on, as you're probably well aware, of how to balance the risks with the benefits of doing that. So, it's going to be a complicated question we're going to have to try and resolve going forwards. The ideal case, I think, would be to develop, and I would encourage any of you in academia to be working on this, is like more interpretability analysis of the current systems, and we're not doing enough of that research on that work, I would say, relative to capability development, so that we could develop evaluation tests for these systems so we can really rigorously know before we release them open source and other things that they're safe in certain ways, what the properties they have. So, so they can be perhaps have some guardrails around them. That would be the best, right? And then you can put them out into the world for people to experiment, but there's constraints around what can be done with them. Maybe something like that, but the problem is we don't know yet well enough what those robust evaluation systems should be yet.
Thank you.
Thank you.
Thank you very much. Thank you all for your questions as well and your attention today. I think we can give Demis another round of applause.
Thank you. Thanks. Thank you. Thank you very much. It's fantastic.